Now, let's talk more about qubits and their states. As we saw before, a pure qubit is a linear superposition of states. So here you see a state psi as an example, and the superposition of the state 0 and 1. So each of these two states associated with a probability amplitude. In the case of 0, it's alpha sub 0. In the case of 1, it's alpha sub 1. And can be represented in vectorial form as alpha sub 1, alpha sub 2 here. The interesting thing here is if we have an equally weighted superposition for a qubit or for a multi-qubit state, then there is no way of telling when you look at that system, no way of telling in advance to which state the system will collapse. Therefore, quantum physics gives us the only random number generator that we have in nature. So you may have used random numbers in the past when you wrote code, but as you know, so everything that we see in our functional programming languages where we have random number generators, this is not really a random number generator. It takes some seed value as an input, and based on that, it produces a number, but this is an algorithm that's running in the background, so it's not a real random number generator. This is important for cryptography, because in the worst case, people could reproduce these algorithms producing random numbers, but with quantum random number generators, there is no way of doing that. There is only a constraint. So in that case, the state psi and the states 0 and 1 should be a unit vector in a complex vector space and subject to the normalization condition. So that means if we look at the amplitudes here, so if we square the absolute values here of the amplitudes, that must sum to unity. So if I give you a brief example here, very simple, let's look at some random complex number, let's say 2 plus 3i, then the complex conjugate of that one would be 2 minus 3i. So remember, if we just look at the amplitude alpha 0 here, then squaring this would be with alpha 0 and the complex conjugate, okay? So what we will get here is 2 times 2 equals 4. Then we have minus 6i plus 6i, and then this cancels out, of course, and then we have plus 9, because I squared is minus 1, it changes the sign here, equals 13. So that gives you only a real number, and therefore the degrees of freedom, they vanish. Okay? So additional degrees of freedom that you would associate with complex numbers, because a complex number usually has 2 degrees of freedom compared to a real number. So another way of representing qubits is by projecting them on the surface of a Bloch sphere. If you look at a classical bit, which can be 0 or 1, and that's it, then you would only be able to find the states of a classical bit here on the north and the south poles. Whereas a qubit, so a superposition state of a qubit with its amplitudes, can be found anywhere on that sphere. And that's the interesting part. So you see, a qubit can have many more different states, or can take many more different states than a classical bit. And so we have an example state here with 0 plus I1 over the square root of 2, which would lie on the equator of the sphere on the positive y-axis. So as we said, the surface of a Bloch sphere is a two-dimensional space, which represents the state space of the pure qubit states. And it has 2 degrees of freedom. And as we just mentioned, it might first seem that there should be 4 degrees of freedom because our probability amplitudes are complex numbers, with each of them having 2 degrees of freedom. However, we remove these degrees of freedom, this additional degree of freedom, by the constraint that we just looked at before. So also, I think I mentioned that in one or two of the previous lectures, a global phase of the state has no physical observable consequences. So if you have a sign in front of a whole state, then it doesn't matter to the state. However, a relative phase that has observable consequences. So a very simple example, just to remind us, is the superposition of the states 0 and 1. If we apply the Hadamard transformation to each of these, then we see for the first one, superposition of 0, we see 0 plus 1, and for the second one, superposition of 1, we see 0 minus 1, which means we have a different relative phase, which makes a different state. So it has physical consequences. A state associated with 2 qubits, we also briefly discussed that one before, but just to remind us here, is a superposition of the 4 possible combinations. So you see 4 probability amplitudes here. And again, to remind us, we don't need to assume that these probability amplitudes are equally distributed, because then the whole quantum computer wouldn't be of any use if we only had equal distributions of these possible states, so equal probabilities of getting them as a result when we measure the system. And it's here again, it's constrained by the normalization condition that generalizes to an arbitrary number of qubits, which is summarized down here. Computational basis in quantum computing is the set of 2 to the power of n classical states, which, if you look at it, so remember, if we have 2 possible states that each bit can take, and we have 2 bits, then it can represent 4 possible states, configurations, however you want to call it. And that goes on. So again, if we have 2 possible states per bits, and if we have 3 qubits, then this can represent 8 possible states or configurations. So, and keep in mind that this is totally different from classical computers, because if I add a classical bit to my computer, to my classical computer, it doesn't double the computational power. But because of this here, a quantum computer, anytime you add a bit, it doubles the computational power. Okay, that's significant. Of course, there are other things to consider here. So I'm talking about a perfect error-corrected quantum computer, which we don't have yet. So if we have qubits that come with errors, then what you could do is summarize multiple physical qubits to 1 logical qubits. So therefore, adding 1 qubit, 1 physical qubit, doesn't double the computational power. So here I'm talking about logical qubits then, which requires more physical qubits. If 2 qubits are in the states as given here, then you can combine them by executing the tensor product, which is something we did before. So let's say I have the state psi and the state phi here, and I have my amplitudes alpha sub 0, alpha sub 1, and beta sub 0 and beta sub 1. So both are a superposition state of a single qubit. Then we execute the tensor product and we get the combined amplitudes here, okay? So and how you represent that in vectorial form is quite natural, as we saw before. Okay, I think there are no other key messages left here. Now let's briefly, again, look at reversible and irreversible classical gates. So before we talked about some classical gates already, and you remember there is one irreversible operation that we specifically remember, which is the erase operation, letting any state of a single bit end up in 0. So no matter if that state was 0 before or 1 before, so which means the result will always be 0. So there's no way of reconstructing the original state from the final state after executing an erase operation. So before we begin, so reversible versus irreversible classical circuits. A classical gate defines a function f from some input bits 0, 1 of length n to some output bits 0, 1 of length n. So you take a string of bits and you produce another string of bits, not necessarily of the same length. If this function is a bijection, then we say that this circuit is reversible. So bijection, just as a matter to define the of definition here, bijection means that for every input to every function, there is a single unique output. So I can't have two different inputs producing the same output. I mean, I can have that, but then it's not reversible because there's no way to conclude from the output which input was given. So bijection means one input per output, or one output per input. So one reason for constructing and considering reversible gates comes from Landauer's principle. I'm not sure if you heard about that in one of your previous lectures, but let's briefly look at it. So assuming we examine a single bit in our computer, then this bit is 1 degree of freedom with 2 possible states. Now, the rest of the computer has lots of other degrees of freedom and can be in one of many states. And one of the fundamental theorems of physics says that phase space cannot be compressed. So what does that mean? Let's try to apply this principle to the process of erasing a bit. So remember, we looked at the erase operation before, and we suppose now there is a physical process, the physical counterpart to our erase operation, which irreversibly erases a bit. So 1 goes to 0 and 0 goes to 0. And since phase space cannot be compressed, if we perform this irreversible operation, then the phase space must bulge out along the other degrees of freedom. So in particular, this means that the entropy of the other degrees of freedom must increase. And if we work through how much it must increase, we will find that it must increase by exactly that. Let me write that down. K, B, T, ln2, which is Boltzmann's constant, the temperature of the system, and the logarithm base 2 for a system in thermodynamic equilibrium. And this is called Landauer's erasure principle. So it means erasing a single bit of information necessarily results in the increase of entropy of the other degrees of freedom by a value of at least kb T ln2. Another way of expressing this principle is that assume you have an observer to that system, and the observer loses information about that system, the physical system. And the observer loses also the ability to extract work from that system. So that's another way of trying to understand Landauer's principle. So it motivates, therefore, to consider reversible computation, because we don't want the entropy to increase. So now today's modern computers are not near Landauer's limit. They dissipate something like 500 times as much heat as Landauer's limit. But certainly there are expectations that this will change as we build smaller and smaller computers that don't become as hot. So now one thing you might worry about is whether the power of reversible computation is the same as the power of irreversible computation. There are some results which basically say that they have the same computational power. And it's nice to see at this point a trick which we can use to compute irreversible functions using reversible circuits. So suppose that we have an irreversible gate F from n bits to m bits. So it takes n bits as an input and m bit is the output that it produces. Then we can design a reversible gate which computes this same function. We just keep the input around. So in particular, we can construct a reversible gate with m plus m bits input which acts as, so if we take x and y as our inputs here, then we leave x as is and apply f of x as a modulo 2 operation, addition modulo 2 to y. So this is what we looked at before with XOR, remember? So this is addition modulo 2, and it's easy to see that it's reversible. Simply apply it twice, and you'll get back the same result. Further, if we apply this reversible circuit element to x0, we obtain x f of x. So which means we have computed f of x in the second zero state here. So we can always turn an irreversible gate into a reversible gate at the expense of having a larger gate. And usually these are called garbage bits, which aren't necessarily used in the irreversible circuits, but we use them in reversible circuits. When we get to quantum circuits for these reversible gates, we'll see that these garbage bits can have bad effects on our quantum algorithms. One of which would be you must be careful of not having your garbage bit entangled with your result before you measure the system with the bits that you use to produce the information that you're after. So that's a problem. So I make sure that you have to disentangle them before. That's one problem that we see here. So if we want to simulate the action of an irreversible circuit from n bits to m bits, is there a way to get rid of these garbage bits? And there is, and this is a trick from 1973. And now we suppose that we have a function which takes the n bits as an input and is implemented using the above construction, which produces garbage bits. So what you see here is a very simple circuit diagram. You will see more of these later in the lecture, but so how you read this is from the left to the right. You see your input bits here on top with X. It's N input bits. You have K garbage bits. We're missing an R here. And you have M output bits. So also starting in a well-defined state in the input register. So here you have your unitary, your function that you implement in terms of a quantum computer, function f, that takes all this, and the garbage bits still remain garbage bits, but you do something with them, so they will end up in a different state than before, and hopefully your output bits, if you do everything right, they end up in the state f of x, so the function that you really want to compute. And now the trick here is to get rid of the garbage bits. So since f is made up of reversible circuits, we can implement f minus 1, so the reversible version, by simply reversing the order of all the circuit elements and then implementing the inverse of these elements. And one important thing to note is that the controlled NOT is a reversible gate and can be used on a zero target to copy the value of a bit into the target bit. So remember, using these two facts, we can implement the following circuit. So here again, if you look at this first part here where you can see F, that's still the same. Then here what we do is apply control NOT bit to the output M bit states. Here we also have M bits on the bottom. And the controlled NOT in that case is really the M bitwise controlled NOT therefore. Okay. So what we do then here on the right is just run the whole thing backward. And here on the bottom, we copied by means of controlled NOT, we copied our input state. We copied that state from up here down to here. So remember how you do that. If we just look at it briefly, let's go back here. So then we remember that the controlled NOT, Cij or C sub ij, on a state 1, 0 copies, so in that case this is my M I bit, so copies the first one, so to say, to the second one, so I will end up with 1, 1. On the other hand, if I apply my controlled NOT gate to the state 0, 0, the resulting state will be 0, 0. So again here I have my mith bit, and so that means, so to say, or you can interpret it as controlled NOT having copied that state to that one here. And that's what we did here in that circuit. Okay. Why are these gates important? So most prominently, and the first time we will see it in Deutsch algorithm, where we turn these gates into quantum gates, which can enact a reversible computation on the computational basis, and they can do that faster. So, or more efficiently, not faster. So you'll see that we will look at a set of functions and some results, and or we look at two sets of functions, and we want to understand which of the sets of these functions produce the result. And turns out that with a classical computer, you need more calls to that function oracle than with a quantum computer. And that's what really kicked off the whole field of quantum computing. So, but we'll look at that in a bit. So we continue here. So if we use this garbage trick that we just did before, we can implement a general irreversible classical circuit by changing the irreversible circuit elements to the quantum reversible circuit elements, and then use the garbage trick to enact a quantum circuit, which and again enacts the unitary evolution of this state here. A very famous example of irreversible gates, which are universal, are the NAND and the NOT AND gate. This is a 2-qubit gate which computes the function here on the bottom, where you have f00 as an input equals 1, f01, f of 0, 1 equals 1, f of 1, 0 equals 1, and f of 1, 1 equals 0. And the interesting question to ask here now is whether there are any classical reversible gates with 2 bits input and output which are universal. And the answer is no. The smallest gate, which is universal for reversible classical circuits, requires 3 bits of input and output. Oh, what sorts of gates are universal for classical reversible computation? Then two most famous are the Toffoli and the Fredkin gates. So a Toffoli gate is a controlled NOT, which enacts the transformation as given below. So you can see that it leaves the rightmost bit alone, except the first two here and here are 1. Then it applies the NOT operation to the rightmost bit. And the Fredkin gate is the controlled swap gate. So very similar. So let's look at a state here where we have a control bit set to 1, and we have the state 0 and 1 here. Then it flips these two and makes 1, 0 out of this, vice versa here. Here you don't see any difference. Here you don't see anything either. Here it doesn't do anything. Okay. Both the Toffoli and Fredkin gates are universal for classical reversible computation, given the ability to use extra scratch bits in fixed states. So one reason to consider the Fredkin gate is motivated by physics. Suppose that the 0 bit and the 1 bit are represented by configurations with different energies. Then with a logic gate like Fredkin's gate, it's possible to conserve the energy of these bits from input to output. With a gate like Toffoli's gate, it would not be possible if the bits have different energies. So it's interesting to go through the current physical implementation of bits and note whether the bits in these devices are implemented in configurations with different energies. Now let's look at reversible operations on qubits. The only non-trivial reversible operation on a classical bit is X. And reversible operations on a quantum computer can perform on a single quantum bit are represented by the action on that state of the qubit of any linear transformation that makes unit vectors into unit vectors. So remember, we want to preserve unitarity. Such transformations are called unitary because they preserve unitarity and they satisfy this relation here. So which is the original transformation times its complex conjugate transpose equals identity. And any unitary transformation has its unitary inverse, such that its actions are reversible. In mathematics, a unitary transformation is a transformation that preserves the inner product. The inner product of two vectors before the transformation is equal to the inner product of the two vectors after the transformation. And more precisely, a unitary transformation is an isomorphism between two Hilbert spaces. In other words, a unitary transformation is a bijective function U which transforms from one Hilbert space to another Hilbert space, which we just talked about bijective functions before. The most general reversible 2-bit operation on a classical computer is a permutation. We had that before. And the most general reversible operation on an n-qubit state is represented by the action on their state of any linear transformation that takes unit vectors into unit vectors. So what we just had before. So this generalizes, of course, to an arbitrary number of qubits. And since now the action of U on the classical basis states is to permute them, its effect on any superposition of such state is to permute the amplitudes, A or alpha sub x here in that case. So remember, these are the amplitudes, these are the possible states. We have n qubits here. Such a permutation preserves the value of the sum of the squared amplitudes. So U takes unit vectors into unit vectors. And being norm-preserving and linear, U is unitary. The transformations swap not and controlled not on C bits are defined in this way for quantum bits as well. So one more thing to say here is that the available unitary transformations on quantum bits are much more general and straightforward extensions of the classical operations. So when we design quantum algorithms, the class of unitary transformations is almost always restricted to ones that can be built entirely out of products of 1-qubit unitary transformations at a time, or that act on a pair of qubits, such as 2-qubit gates. For a reversible classical computer, at least one 3-qubit gate is needed in order to build up general logical operations. And the quantum extension of these 3 classical bit gates can be constructed out of a small number of 1 and 2 qubit gates. And remember that unitarity is a requirement. It's just how nature has given it to us. It's very easy to imagine a simple classical model for a qubit, particularly if its states are restricted to real linear combination of the 2 computational basis states only, which is what we looked at mostly before. It's also easy to invent classical models for NOT and Hadamard 1-qubit gates that act linearly on all the 1-qubit states of the model qubit. There is no classical model, or no classical model can extend a controlled NOT on the 4 computational basis states of the 2 classical bits to an operation acting linearly on all the states of 2 model qubits. And it's remarkable that this is not possible, or that it's possible to fabricate any controlled NOT gates for a pair of qubits. And all classical computers, as remember, they work in fundamentally the same way, whereas quantum systems are fundamentally different. The size of the problem goes up exponentially in the size of the system, making them hard to simulate. That's also what Richard Feynman in 1982 proposed. So in 1982, he gave that speech, or he was asking the question, so why it's so difficult to use quantums or to simulate quantum systems with classical systems. So does that also mean that if you have a computer that exhibits quantum effects or uses quantum effects for computation, that this computer is more powerful? And this, along with the algorithms that follow, kick the whole field of quantum computing off. A classical computer, as you know, uses bits or strings of bits to do a computation on the most fundamental level. On a quantum computer, we replace this with a quantum state. So each digit that you see here on top is a 2-level quantum system, the 1-qubit that you remember from before. As long as you don't look at it, you are in a superposition of states. So, and this is the formal way of writing these superpositions of states down or representing it in vectorial form again with the probability amplitudes psi sub 1, psi sub 2 until psi sub n. Operations, as we remember, can be represented as matrices, so unitary matrices. The allowed operations, as we had a couple times before already, must satisfy this condition here. Any allowed operation is reversible, and using U dagger on the original U applied to a state will restore the state. Okay. A special case is the permutation matrix. The permutation matrix only changes one computational basis state to another. Examples of permutations that we'll briefly talk about include the NOT operation. We looked at that matrix before already, so which takes 0 to 1 and vice versa. The controlled NOT that we also looked at before, which performs a NOT on the target quantum bit if the controlled quantum bit is in the state 1. Otherwise, it does nothing. And here, what you see on the left, this is the way to represent the controlled NOT bit in a circuit. So these lines here from left to the right, that's how time evolution goes, from left to the right. These represent the qubit states, the qubits. This black dot here represents the control bit for any other operation that follows down here. But in that case, it's the controlled NOT operation. That's how the controlled NOT operation is represented. The matrix, we remember how we got that before. We constructed it for the swap gate, and I hope you try it out for the controlled NOT gate as well. This is how you get it. The Toffoli gate is the next one, is a controlled NOT gate. Okay, so it performs an X only if both controls are in the state 1, as we saw before. And it's given by the matrix here on the right. So in a circuit diagram, again, it would look like, so you could imagine you have one control bit here, one control bit here, and I have one target bit here. Then what it would give you in the end would be this state. Okay, so this is how you read it from the left to the right in your circuit diagram. These two here represent the control bits. This is the target bit. And here you have the matrix on the right, which can be constructed in the same way as we did construct the matrix for the other operators. The NOT AND gate is universal for classical circuits and acts as below. So we looked at it briefly before, where we have two input bits here and we have our output bit here. So it takes 2 bits as an input and produces 1 bit as an output. And we see that we can perform the same operation using a Toffoli gate. Okay, so here we have A and B, our input gates, still input states. We have A and B as an output states here. And on the bottom here, we start with a 1. So that's required in order to make this happen. So in order to make this Toffoli gate work as expected. So we see the 1 here and then producing the output value here, the output state here. So I encourage you to give it a try. It's fairly simple and fairly straightforward. So we can convert any classical algorithm into a quantum algorithm, replacing the NOT AND gate with Toffolis and keeping the extra qubits. Talking more about turning classical into quantum, any function we could calculate on a classical computer, we could also compute on a quantum computer with the addition of some extra garbage registers. Remember when we looked at the addition modulo 2 or the XOR, and we had an additional function here. So here it's represented by the extra data, the extra garbage data that we use on X. Okay. So this can be turned into a computation that does the following. So we have our unitary transformation U sub f here, which, so when you see U sub f here, that represents the function. So you have some function here that you turn into a unitary and then you call it U sub f here. that you apply to your X gate. And here you have your zero state, returning back the original X and the f of X for the target bit. Okay, so that means in that case, one way to look at it is also by thinking about the identity transformation that we considered before. So we leave the original state as it is, but we do something to the target state based on the original state. Um, so the method here that we have is we add an unsillabate and perform the program as above to give the result that we expect. So for ancillas that are usually that are not initially zeroed, we can perform the XOR gate as follows. So we had a look at that before. When you do the addition modulo 2 here, so you have your input, your U of f here, your function, and what this does is it leaves the input state alone, but it takes the state B and applies the f of x, so taking that input value here into that function, considers it into that unitary, and makes some addition modulo 2 based on the result. Now, what if we start the state in a superposition? So the superposition, as you remember, is in that case, it's an equally distributed one. But in a superposition for n qubits, we have evaluated an exponential number of different values of the function. So that means for all possible configurations of that system, we now did that evaluation at once, which is remarkable. There is no classical counterpart to that. In a classical machine, in the worst case scenario, you would have to do that in sequence, in the worst case, in sequence for all the possible configurations of the system. With a quantum computer, you evaluate it for all possible configuration of the system at once, which is one reason for why quantum computers are so powerful. Another part we need to talk about is interference. So we can't just calculate many values of a function. We need some way to interfere them to obtain some global property of the function. So we need non-permutation gate. The Hadamard gate, for example, is in a matrix representation as given here, which results or takes this definite state 0 into the superposition state. So another way of writing it, we wrote it down this way before for the superposition of 0, which is exactly the same as this one here, and same for 1 with a different relative phase here, okay? And you know Schrödinger's cat, right? So Schrödinger's cat, this famous example, so this thought example that he gave based on or gave to understand or make people understand the superposition better. So he had a cat in his thought experiment. He had a cat in a box, and there was a gas cylinder with poisonous gas in that box, and it was triggered from the outside with a quantum effect. So the radioactive emission of some radioactive material, so which could happen or not. And if you don't look at it, it happens. So both happens. It's emitted and not. And so what he wanted to explain with that is, as long as you don't open the box, the cat is both alive and dead. So the cat, you don't know for certain, for sure, if it's alive or dead based on this quantum effect. And the theory would predict that also macroscopically, it would be alive and dead at once in a superposition of that state. Once you open the box, you look at it, you will find the cat in a definite state, alive or dead. Which is, of course, not what really happens, but he used that to explain the superposition. So we can't just calculate many values of a function. We need some way to interfere them to obtain some global property of the function. So on universal sets of gates that we have to our avail is the Hadamard gate that we already looked at, together with a Toffoli gate is universal for real unitaries. Pi over 8 or T gate together with the Hadamard and the controlled NOT gate is universal. So that means with a combination of these gates, you can execute any or run any transformation on the state. So I guess it's not big news when I tell you that computers that we know that we use are built from networks of logic gates. Quantum computers use logic gates in a similar way. So networks are constructed to perform certain operations. And there are many more possible quantum gates than classical gates. So in theory, there are infinitely many, but in practice, we don't use infinitely many. And they must all be reversible, as we know. And this is because we want to represent them in terms of a unitary matrix. And why we have to do unitary operations, we already learned previously. So an example that we already looked at before is the quantum NOT gate, so which you can see here on the bottom, applied to a vector a sub 0, a sub 1, it makes a sub 1, a sub 0 out of that one. The most commonly used single qubit transformations that we also looked at before, the Pauli matrices, if you remember, are these ones. We have I as the identity transformation, we have X, the NOT transformation, we have Y, and we have Z. Z changes the relative phase over superposition in standard basis, and Y is a combination of ZX, so it's a negation and phase change. You can try to construct Y out of ZX, so if you just do that multiplication, you will get the Y gate, this one here, okay? The quantum analog of the NOT gate is therefore easy to picture, and other classical gates that we know are not so easy to transfer to the quantum world. Okay, so the rest here is not big news. We have reversible gates and we have to have reversible gates, and why we do that we talked about before. Now let's have a closer look at the C-NOT gate, controlled NOT gate, and how to construct this. So remember how we constructed the 2-qubit NOT operation, which was just done by taking the 1-qubit NOT operation and executing a tensor product with another 1-qubit NOT operation. And remember how we looked at this from the very beginning. So we want to see how the states should change given these initial conditions. So that means here, if the original state of the control bit is 0 in the first one, then apply identity to the second one, which means leave it alone. However, if the state of the first qubit here is 1, then apply the NOT operation to the second one. And let's quickly have a look at how to construct this gate. Let's just continue here. Let's see. So the controlled NOT operator is given by looking at the original state. See if it's 0, then we do identity to the second one, plus if the initial state is 1, we do a NOT operation on the second one. Okay, so let's look at this part first, which means so we construct the projection operator on the state 0 as we did before. So let's start from scratch and say 1 0 1 0 becomes 1 0 0 0. Then we take that one, create or execute a tensor product between identity, which is 1 0 0 1. So if we quickly run that, we have 1 0 0 0. We have 0 1 0 0, and all zeros here. Okay, so now let's look at this part here, which is the outer product, the state 1, so which is 0 1 here, resulting in 0 0 0 1. Then if that state is 1, we apply the NOT transformation to the second qubit, which is given by this one here. And if we quickly run that through, then we'll see we have 0 0 0 0 for the first one. We have, you can look at that, all the zeros for the second one. We have 0 0 0 1, and for the last one we have 0 0 1, 0. Okay, now we have to add these up, which as a result gives us this one here. Which is the controlled NOT operation. Okay, so this is how you construct this gate. And let's move back to that gate here. Here we have a different way of constructing it. We just use the bracket notation. So what I just showed you was the matrix notation, but of course you can also do the bracket notation. So if we execute that, so remembering that the identity transformation is this one here, and remembering that the NOT transformation is this one here, remembering that so how the inner product behaves, that if you take the inner product of a vector which itself, it results in 1. If you take it with another vector, if it's orthogonal to each other, then it will result in 0, which leaves you with this one, which is the controlled NOT operation in bracket form. So now you have two ways of constructing that, which is straightforward. So it's fairly easy still to do it in the matrix form, but if you have bigger matrices, it becomes a pain, so maybe easier to construct it that way. No surprises here, so that's how we define the controlled NOT operation. So here you see again what it does to the amplitudes. So if you have 1, 0 here, first one being the control bit, it makes it 1, 1. And same here, when you have 1, 1, it makes it 1, 0. It's important for entanglement. So what we can see here is the construction of entanglement. So you remember the states of an entangled 2-qubit state. So remember this state here, that one, we talked about it in the beginning. If you write it down in vectorial form, then what you have is this one. So these are the probability amplitudes. And if you try to construct it from a tensor product of two single qubit states, you will never get this result. So because these amplitudes here in the middle are 0, which in turn, if you do the multiplication, would indicate that one of these must be 0, 2, so and therefore these two could not be 1 over the square root of 2. So if we look at that example here, how that works, you see the controlled NOT operation applied to a superposition state. This is the first one, the control bit, okay? And here, this is the target bit, so what we want to achieve. So, and this results in the following. So if we take the superposition state, if we execute the multiplication here, then you get this one. And once you did that and apply the controlled NOT operation, you get this state. And remember what that means. That means that this state is not separable. So you cannot deconstruct it. So as you cannot construct it from two single qubit states, you cannot deconstruct it into two single qubit states. So what that means is that you cannot treat these qubits as separate systems anymore. So if you do something to one, it also happens to the other. So they are entangled. A more elaborate way or a more elaborate gate is the controlled NOT gate, Toffoli gate that we briefly talked about before. And here again, you see the states, the possible input states. So it only has an effect on the last two here, because here you have the first two control bits set to 1, which means the target bit here, this one here, switches or flips. And again, like we did before, you can construct the matrix either in the bracket notation or in the matrix form. Still, with the matrix form, it's not too complicated. So I encourage you to look at it. The swap gate, controlled swap gate, which we also briefly mentioned before, the Fredkin gate, you can easily construct it with So from these input states here and the given output states, so what it does is, if the first one here is 1, okay, then it swaps the other 2 qubits in that case, or the other 2 bits, classical one if applied classically. So, and then there are a couple of quantum gates that have no classical counterparts. So the controlled NOT, controlled exchange or swap gate are all gates which can exist in both classical and quantum worlds. But there are many other gates with no classical analog, such as the Y gate or the Z gate. As we remember, together with X, they are known as the Pauli matrices. Another very famous example, of course, is the Hadamard gate, which constructs a superposition of states. There is simply no analog to that because there is no superposition in classical computing. So you can have probabilistic states, but no superposition, no quantum linear superposition. A couple more gates are the phase gate S, which you will encounter a couple of times, then the T gate, which also applies a rotation here, another, the RK gate rotation. And these seem a bit arbitrary, but they will be useful in various quantum algorithms, so we'll be using them later. If we now look at quantum circuits, so far we have represented quantum gates with matrices. We played with the Pauli notation, the Dirac notation, but it will often be very useful to adopt a graphical representation, such as the one that's described here in pictures. So what we see here is an input register. That input register, I can have n qubits, so it's not limited to 1 qubit. Here we have a unitary that we execute on that input register. So we have this well-defined input state that we understand and know. So let's say we set everything to 0. Then we apply a unitary to that input state, and what we get is Q, so a new output state, again with n qubits. Each line that you see here on top, these ones that represents 1 qubit, for example, for the NOT gate, it would look like this. So you have a single qubit NOT gate. So you have your qubit I here. You run from the left to the right. That's how time goes. So you say you evolve that state. You apply the NOT transformation, and you get as a result Q as an output. A simple example circuit that we have here is a state that applies, so you have an input state and you apply the NOT transformation twice. So what you see here, you have I run the NOT transformation on it, then you have I prime as a result. You don't look at it, because if you look at it, meaning in terms of measurement, then whatever that I is, so if it's not a definite state, if it's a superposition state, then it will collapse, okay? So then you apply the second time, and Q should then be again the same as I if you do that. This is not a useful gate, this is just something that I wanted to show you here. And we run through that, okay? So I prime means the application of X of NOT to I. So remember the NOT transformation is that one here. We assume we have a state with amplitudes A0, A1. It creates that one out of that, so it flips the two. Because it's not I, then we have Q, which is given by NOT on the state I prime. And so I mean we can apply it, and we get back the original state here, okay? So those two are equal. Which is what we would expect from applying the NOT transformation twice, since we know that the NOT transformation, like all the other gates that we apply in quantum computing, are reversible. There are different ways of writing this down. So one is this, writing it twice, x squared, so by applying that twice, okay? So, and you can also run the gates, execute them here, so, but careful. So the sequence may matter, so here it's useful to check if the gates commute or not. Another example is the controlled Z gate, which we will encounter again when we talk about teleportation. So remember when we talked about the controlled NOT operation, the controlled NOT operation also had this control bit here, the black dot here. And so that means this qubit here on top is the control bit. And here on the bottom, we have another qubit. which we apply the transformation Z2 or Z2. So like we looked at it before, we can do a couple of transformations. So we have, in that case here, a circuit that runs the controlled Z operation, giving you the state I prime, and runs then the controlled NOT operation, giving you the state Q. And again, we can construct a gate on that input state. So we take these two gates that we have, and we note the order and construct this matrix from it. Okay. Why do we do it that way? So that's also important. So when we look at the order, so we have controlled NOT and Z, controlled Z. We do this because clearly this one, controlled Z, is applied first. This one is applied second. Okay. So that's very important. So note the sequence. So this one is applied first to your state, the other one second. That's why we construct it that way. So you read it in that case from right to the left. So in the algorithms that we will study next, we'll need to be able to analyze circuits which contain both 1 and 2 qubit input gates. This is a little more complicated. And so let's look at that example here. So we have an input resistor, I, and we could say it has the state 0 here and the state 0 here. And we could write that down as 0, 0. So that's the very same way and very same state that we have here. But then we apply the Hadamard transformation to the first one only, giving us back what we had as an example before, 0 plus 1. And then the second one, since this on top is a connection via tensor product, is given by that one. Okay. So this becomes a little more complicated then. So we have our superposition here, and we have I prime, which is given by that state here. And then we apply controlled NOT operation. So it's the very same thing that we just did before with entanglement. And the resulting state that we get is the entangled qubit state that we saw before in that case. So as I just wrote it down here. But if we apply to different input states, so not necessarily we do start with everything 0. So with 0, 0, we get different entangled states. So and the first one that we already know of is that one here. Then the second one gives us this one, third one, and fourth one. Okay, and the matrix for this is given by m equals 1 over square root of 2. So that's how you can construct the matrix for this state. So again, I encourage you to try that out. It's fairly straightforward again, but very possible. So now that we have m, we need to also apply the controlled NOT operation. So we're still working on the state I prime. So if I go back here, we're here now. So if I go forward again, we see the state controlled NOT applied to the m that we just constructed before, multiplied by m that we just constructed before, we get this final transformation, which includes the Hadamard transformation and the controlled NOT operation, resulting in that these entangled states that we see here. Okay, so and for all of these, one fact is true. None of these can be deconstructed into single qubit states, and none of these can be constructed from single qubit states by taking a tensor product between these single qubit states. These are also known as maximally entangled states or Bell states. So if one qubit is measured, we automatically know what the other one is without measuring it. That's very important. That's not always the case. For states that are not entangled, this is not true. All right, then The only thing that remains to say for today is thanks for listening in and your attention. We conclude this with a quiz. Again, I have the answers at the end of the slides, so please try to work out these questions on your own. And if you have questions, as always, please feel free to reach out to me. Thank you very much.